For us programmers, it's a morning still. Safe Kotlin. What do I mean by that? What is safety in terms of programming? You might have heard about type safety. That is a set of mechanisms that stop us from using methods that are not in an object. You might have heard about memory safety. That is a set of mechanisms that help us with memory management. You might have heard about null safety. That is a set of mechanisms that stops us from calling on nulls. So seeing that, you might have a vague idea what is safety. It is a set of mechanisms or a design that stop us from doing mistakes. Safety should not be mistaken with security. So safety is concerned with internal threats, so errors, bugs. When security is concerned with external threats, so hackers, viruses, etc. So when I think about safe Kotlin, I think about best practices for us to make our programs less prone to errors, more correct. Correctness, I think, is the most important trait of programs. And this presentation is based on my book, Effective Kotlin, concretely on the first chapter called Safety, and we'll go through next items. It's a very short overview, as this is like 70 pages or something, so there is still a lot to discover in this topic, but I hope to give you the core ideas. Starting with mutability. Mutability is known to be a huge concern for safety since like 70s. Structure and implementation of computer programs, very classic book, was very much about mutability, and we know it's problematic. Mutability starts when we have either var in Kotlin or a mutable object or other kind of side effect. So something that mutates and we depend on the state. Though it's very hard to design programs without mutability, mutability is known to have many problems. For instance, mutability makes it harder to reason about the code. We need to understand all possible states. When we debug, we need to check what is the current state. We need to test all the different kinds of states that we might be in. It also prepares proper synchronization in multi-threaded programs. So you might seen something like that in your past when you make multiple threads, and all those threads are modifying this very simple variable I. It is highly unlikely that there will be no conflicts. So it's highly unlikely that on the end, print num will print 1000. It should be rather maybe 9999. It will be rather 973, 84, 69, I don't know. It's all race conditions, and it's absolutely unpredictable. If you think that coroutines help, not really. Coroutines have their mechanisms, but these critical sections, they still need to be saved. They still need to be managed. And so just using coroutines does not really help. We have less threads operating, but still we might have as many conflicts. We need to synchronize mutability, and this is always a problem. Another thing is that mutable elements are harder to test. If you have an object like a bank account, what is the result is not only about what you put in an argument, but also what is the internal state. This one is having a very simple state, just some amount inside, some balance inside. But it might have more elements, and all those elements, all the variants of all those elements should be tested, and if you do not test them, you do not know how they behave in some strange configurations. So testing is much harder for mutable objects. And finally, when state mutate, it is common that something else needs to be updated. If you have a list with data, when you change this data, you need to update list. A very simple example is, imagine that you have a sorted list of users, and then you modify one of those users. You change its ID. This list was sorted by ID, and so right now, item is at incorrect position. If you do not modify, if you do not inform the list that it should be sorted again, then you have incorrect position for this object. And if you ask if an element is in this list, and this element is in this list, but if you ask for that, most searching algorithms will look at incorrect position and they won't find it. So it's a simple illustration of problem that we need to update outer objects when we modify something mutable. But how to deal with mutability limitation? And Kotlin here gives us some really useful tools. My one more conclusion was that, Kotlin gives us some important tools. First of all, it distinguished val and var. So val is something that is read-only, var is something that is mutable. It also made a distinction between mutable and read-only collections, and it introduced copying data classes. So let's talk about them from the beginning. When you use val, it means that something is read-only. It cannot be modified. It doesn't mean that the property is immutable. First of all, it might hold object that is mutable. And second of all, it might be defined by a getter, and so it might give us a different value every time. Clearly, we prefer val over var, but we prefer final val, one that does not really mutate even more. It is even possible to make to overwrite val with a var that is on a child. Another mechanism is the distinction between read-only and mutable collection. And again, those are not immutable collections, immutable lists, because under the hood, pretty often, mutable lists are used. So actual object is mutable, but it is hidden from behind an interface that offers us only immutability. This is the best option for us because it gives us the maximum of flexibility. We can use whatever object do we want, and we can use platform-specific objects, and in the same time eliminates most of the problems. So the real problem, most of the problems is the mutation itself, not the fact of the possibility to mutate something. And when it is limited, we eliminate most of the problems. So it's like both maximum flexibility and in the same time maximum, and the same time high safety. The same as with vals. Vals are not immutable, but thanks to that, they give us a lot of freedom and encapsulation, and we can change them in the future. Of course, it works as long as no one tries to hack it. So if you do something like that, try to upcast a list into a mutable list, behavior is, I would say, might be unexpected. At this moment, on Kotlin.js, it would actually modify it because array is used under the hood. In Kotlin JVM, it will throw unsupported operation exception, but I have no idea how will it behave in the future, in a year. There are experiments with persistent collections, so maybe this if will not happen at all. So this is something that should never happen. When we have something hidden from behind a list or from behind other read-only interface, we should respect it, and we should not force to upcast it into something mutable. And if you want to have a mutable list, you should use two mutable lists. Only then we are secured. And the third important thing is immutable objects over mutable objects. Immutable objects, except of profits of having less mutability itself, has other profits as well. So mutable objects are easier to reason about because once they are set, you checked what is their state. You do not need to check how they change internally. So they are more predictable. It is easier to parallel. They can be shared between threads, so it's easier to parallelize program. Can be cached. They are always the same. It's not a problem to cache them. And we do not need to use defensive copies. So this is an old practice known in Java. In Java, every list was mutable. So this is how we would implement things in a Java-like style, a mutable list. And when you return something, you return a mutable list. This is highly unsafe because you are leaking mutation points. So even though store users is private, you are exposing it by returning a reference to that. So someone might accidentally modify it later, and then you might be surprised that your internal state of your object has changed. So the Java solution was defensive copying. A bit more Kotlinish solution is hiding something behind an interface. So all we need to do is just declare map as a returned object. Or maybe you might consider about using a read-only map at the first place, or read-only list at the first place. And finally, a small bit that they can be used in maps and hashes. This is common to the fact that other elements needs to be notified. Imagine that you have a set and you add an instance there. And then you modify this instance. Even though this instance definitely is in this set on the first position, when you check if it is there, your collection says, no, it's not there. So how so? The problem is that mutable set uses hash map under the hood, and so it placed your object in some bucket, and then it should be placed in a different bucket, but you haven't updated your hash set, and so you cannot use mutable objects in sets, in keys, in maps, in any data structure using hash set under the hood. In general, immutable objects are perfect material to construct other objects, but they are just hard. It's harder to operate on them. And one solution to this problem was to make immutable objects and provide a set of functions that was creating a copy with something changed. It was clearly pretty hard solution to make method for each property, but instead Kotlin introduced a copy in data class that lets us create a copy with something changed. And it is a good support for immutability. We really like having immutable data classes, and when we need to have some updates, we are using copy to modify, to create a copy with something changed. It is good to understand that there are different ways how we express mutation points, and they are all, in some ways, they all have some pros and cons. So I am often asked, do I prefer val and mutable list, or do I prefer var and read-only list? And from my perspective, there is no such a big difference between those. They both have one mutation point. It's only placed in a different position. When we have mutable list, modifications are faster, more performant. Although when we have read-only list and mutable property, then we can easier track changes, so we can wrap it in observable, like this one, and see how values change. So both approaches have their pros and cons. I would say this one is better, probably better for most properties, and mutable lists are probably better for most local variables. But from my perspective, there is no such a critical difference. But the big thing is that we should not make like absurdish or unnecessary mutation points, like making val and mutable list is something that I would like to never see, because then something can be changed in two ways, and we can never predict how it's changed. And some things like plus equals is not valuable because of ambiguity. And so, to summarize this very long section, we prefer val over var when we can. We prefer immutable over mutable. The same with properties and with classes and objects. When we need to change a data class with copy is a good option, and we should design our mutation points wisely and do not produce unnecessary ones. And we should not expose them, not leak them. Another another side of this story is a scope. So one way to limit both visibility and modification is using a narrower scope. So scope is a scope in which something is visible. So in here, A is visible everywhere, but B is only visible inside phys, C is only visible inside lambda expression that is assigned to biz. We have a variety of tools we can use to limit scope. So here, user is clearly having unnecessarily wide scope. We are risking that someone might use it outside of this for loop. It's clearly better to make something val local. Some people have habits of doing things like on the first snippet because they believe it's an optimization. But if you spend some time with JVM bytecode, you might notice that such an optimizations are generally done by compiler itself. You don't need to make them yourself. And in general, low-level optimizations, it's not worth to do them because compiler generally can do them better than you do. It's also very useful to use control structures as expressions. So if, when, try, catch, to set something, it's clear that user is set, and it's clear what way is it set. And finally, I would like you to take a look at this example. This might look quite hard. It's a sequence builder. It's a Aristotle's CF in a very simple in a very short snippet. We are having infinite numbers starting from 2 ad infinitum, and while true, we are taking first one. This is a prime number, and then we are dropping this number, and we are filtering out all the numbers that are divisible by this number. So it's a very classic exercise. It was an exercise on my Kotlin coroutines workshop. And though what I've seen people doing pretty often is lifting this prime number up and making it var. The only problem with this micro-optimization is that the result is not correct anymore. So it used to be prime numbers. Now it's 2, 3, 5, 6, 7, 8, 9, 10, 11, 12. So why it doesn't work? Anyone? Marcin. It's my reviewer, so he definitely knows. That's right. We have unintentional capturing. So we are now we are not filtering out all the previous numbers. We are always filtering out the same number. So prime is changing its value. It's only one value. It's only one variable that is captured and used in all the filters. So we are always filtering out the last prime instead of all the primes. So unintentional capturing, Kotlin allows implicit capturing, and unintentional capturing is something that we need to be aware of when we are using local variables. And one way to fight with that is minimizing scope of variables and preferring val over var, also in local scope. Okay, let's talk about typing, because I believe typing system is great and it's very useful, but to truly unleash its possibilities, we need to use it. And one problem is when we have null safety that stops us from calling on nulls. But one problem is when we are interoperating with Java. So when we are interoperating with Java and we have something that is annotated as nullable or not null, we trust it is correct, and we use correct nullable or not null type. But the problem is when we operate with Java and it is not expressing if something is nullable or not. So we do not like this situation, and we like to prevent it using a variety of different annotations. But if anyways we have some Java interface or Java class returning an object with unknown nullability, when we get that in Kotlin, it's a special type that we do not really like. It's called platform type, and it still can be set as either nullable or not null. And okay, it can be set, and I think it should be set, because if we keep it unset, then at every point you can decide again and again if it is nullable and not null. If you set it to not nullable, if it is null, at least you have a warning immediately. In here, you are still kept in unknown state, just like in Java. And so, see the difference between those two. In the first case, we are inferring platform type. And we might use this value many times safely. And then a new developer comes into our project and accidentally uses that unsafely, because nothing stops him or her from doing that. And he or she has this null pointer exception out of some expression, probably hard to track back, probably passed through some methods, I don't know. When you eliminate platform type and you set type immediately, even if you are wrong, you also has null pointer exception. But it's clear where does it come from, and it's easy. It's clear how should we fix that. And so my suggestion is to eliminate platform types as soon as possible. Do not infer them. Do not let them propagate. An extreme case when we propagate platform types is when we infer it into the result type of a method in an interface. So this is a platform type, so we can still decide if it is nullable or not null. So in the declaration side, we might decide it's nullable and return null. In the use side, we might decide it's not nullable and use it directly and have runtime null pointer exception. With null produced in Java and consumed in Java. So to be fair, we have a warning for that, but to be also fair, people often do not care. And I believe we should eliminate platform types as soon as possible, because they are badly interoperating with our systems, they are dangerous, and they should not be in our programs. And another problem that can be visible in here is actually connected to my other item. This item is connected with the idea that type inference is exact. So when you set animal to zebra, you cannot set it to animal later, which is a superclass, because it's the inference infers the closest possible type, the concrete type, the exact type. Of course, the solution is simple. Let's just set type. But not always you can do that, especially if this is part of external library. So imagine for a moment that you are a library creator, and you are producing cars. You are making interface to produce cars. But you notice that most of your cars are of the same type. And so why not making it the default car? And then you decide, hey, I can skip type because it's set anyway. And someone on the other end decides, hey, this default car can also be inferred because, it's a car. And like, congratulations, now your car factory produces only one type of a car. So this is exactly what happened in communism in Poland. And I don't want it again. So item 4, do not expose inferred types, especially if you are a library creator, if you are exposing something, if you have a part or API, a public method in a public class or interface, please specified type is an important information, and it should be clear. And the last part, my favorite, I think, is connected to expectations, because it's not uncommon that we have some expectations that we want to express in our code. And Kotlin gives us a special ways to specify or express these expectations. So there are 3 most universal ways to specify expectations. Require is a universal way to specify expectations on arguments. Check is a universal way to specify expectations on state, and assert is checking something. You probably know it from unit tests. Plus, we have some other mechanisms like Elvis operator with return and throw. It's very clear and also useful way to specify some expectations on lack of nullability. You can see them used in this function. So this is a function popping some numbers out of a stack, and we require the argument to be smaller than size. If it is not, we want to throw an error. We check if it is open. If it is not, we want to throw illegal state exception. And on the end, we always expected that the return type, the size of a return list, is equal to the size, to the num from the argument. And this is something that won't be checked on production, but this is something that should be always expected on all your tests, or all your unit tests, etc. So we set up expectations this way because it makes them visible. Like they are clear. When someone sees our function, he can see exactly what is expected, even without reading documentation. If they are not satisfied, we are not letting this any further. So we are not letting this incorrect data modify our internal state, what might be dangerous. We stop that immediately, and we do not allow incorrect arguments, state, or situations. And finally, to some degree, our code is self-checking. So like we are moving our unit tests into code, and we are making them like everywhere. So everywhere, everything is checked. And also when you read this code, there are some things you can be sure of because they are expressed, and you are sure that they must be true. So there is some sureness you have when you read such a code. And to some degree, it's also useful that it gives us smart casting. So let's think about require. When we have a factorial, we can require argument to be bigger than 0. If it is not, we want to throw illegal argument exception. This is what require does if expectation is not met. When we ask to find clusters, we might require list of points to be not empty. When we want to send email, we might require user to have an email and require this email to be valid. If it is not, it is a user responsibility to check if it is correct before using our API. This is how require looks inside. It is trivial, so it has contract, which is very useful, and it throws illegal argument exception. And we can also specify lazy message, so a message that should be in this illegal argument exception. Another block is check, so check state, throws illegal state exception, so we can check if, when we ask to speak, we can check if our service is initialized. When we ask for an info, we might check if user has token, or if there is a token. When we ask for the next element, we might check if a collection or something or a repository is open. So those are expectancies that are specified in our documentation, and here we are checking if they are met. And finally, assert, the title I see is incorrect. It should be assert that checks something to be true. It's known from unit tests. We use assertions on unit tests, and by default, they only run on unit tests because they require some flags, so they will not be checked on production. But it is not. It is also good practice, very, very popular in Python community, to place assert in our code if something should be always expected on the end. So it is like placing it after every test. So why placing it after every test? If we can place it in our code, and then it will be checked by default in every test that we have. And also it can be something that when we read this code, we can be sure of at this point. And yeah, it throws assertion error, and to enable that, we need to use a special option. When we throw errors, we prefer standard errors. You already know illegal argument, illegal state exception, but there are also other standard errors, and we generally prefer to use them instead of our custom ones, because they are known, they are expected, and we are familiar with them. They are also all inherited from Java, and so Java developers know them well. We sometimes need to throw our own exceptions if we want to express something that is not expressed by any common exception. But at first, we should look for some standard one if it can express what we want to express. But my general rule is to avoid exceptions, because exceptions in Kotlin are unchecked exceptions, and they are used to notify user about an incorrect situation and something that should not happen in normal circumstances. If we want to inform user about something that is to some degree expected, it's better to make functions that express incorrect or lack of result in a safer way. Like, for instance, returning null or returning a failure. So there are a few ways how we can deal with function that cannot get result. We can return null or some sealed class. We can throw an exception on, or we can return some default. I think we should think about the first one, returning null or a failure. Here is function reading an object, and we assume that it might be unable to read this object. And the first one, read object or null, in case of inability to read this object, just returns null. Null is a universal message to say that we couldn't read this object. The second one also has in its API information that it's possible that it cannot read object because it returns result that is either a success or a failure. It might be Kotlin standard library result. I mean, not at the moment because currently it's experimental and not allowed at this position, but probably in the future it will be. Or you can implement it yourself. It takes 3 lines, so it's not a hard thing to do. Both those needs to be handled. They must be handled. You cannot just ignore them, unlike you can ignore exception and propagate and break your system. Both nullable and result must be handled, and they are both very easily handled. So both of them are very, very easy to handle. We generally prefer null when we do not want to express anything specific, because null is not having any data, in opposition to failure that can hold some data, like concrete error. So it can hold many possible problems instead of just the fact that something went wrong. It's really good to give users options. Inspire with standard library. When you get something from a list, you can get, and then you expect it is there. And if it's not there, it's something that it's unexpected situation, and you throw index out of bounds exception. You can get or null when you assume there might not be something in this position, and then you are forced to handle it safely. Or you can have other options like get or default. The same with many other things like first or null, first or return, etc., etc. So when we get nulls are generally, this is one of the most popular ways how nulls are used. Nulls are generally informing about lack of something, inability to give us result, or something is either unset, or that we just couldn't produce a result correctly. And when we get null, we need to handle them safely. We cannot just call something on a nullable type. We need to either use something like safe call, smart casting, or not null assertion. There are generally 3 key categories how we can handle nulls. We can either handle them safely, we can throw an error, or we can just refactor to avoid this nullability if it is not expected. So think about the first 2. Starting from the first one, handling nulls safely. We say that it is safe. It is safe from the perspective of user, because user will not see any error. We are doing nothing when something is null, or we are just skipping such situation. We are returning. We are somehow avoiding problems when we have null somewhere. We call it safe call, but I'm not sure if it is so safe in all situations. So imagine that null at some position is highly unexpected. It might be a syndrome of a serious problems. And silencing it like that is not the best idea. If null is unexpected, if null might be an information for you, then we should use the other approach that is throwing an error. And we already know how it can be done. We have require, we have check, we can throw an error, we can use throw, or we have this not null assertion that I also criticized in my book, but I don't have time to go in detail. In short, it's a lazy option. It's generally better to provide a concrete error instead of generic not null assertion, null pointer exception. And those two approaches are two flips of the coin. They are defensive and offensive programming. Defensive is like handle that safely without any errors, and offensive is like make it loud when something is wrong. And they seem like the opposite, but they are both needed in good systems. So in some situations, we can handle something safely, and safe handle is a better option. And in some situations, we should express that something is expected and not let it any further. And offensive programming is better. And I think understanding those two and when they should be used is one of the most important elements of safe system design. And one bit at the end, when you have something that is closable, we have many such things in Java standard library, for instance, buffered readers. We should close it in finally after using that, but it is incorrect approach because this close can also throw an exception. So a better approach to do that, there is a function introduced by Kotlin library that handles that correctly. It is called use. You can just wrap something closable with use, and then it will be cleaned up after it is used. We can also, the argument of use is the receiver, so we can make it slightly shorter. And what is more, instead of use and getting a sequence, we might just use lines and operate on that directly. And also use lines function, which is a good function to read from a file, can be used as an expression, so everything can be shortened in the following form. On all that, I use sequence to operate on files, what is also important because files can be big, so operating on that as a list is dangerous. It might take too much space, and at every processing step we would need to hold that, what would be unsafe. And so we always iterate over file using sequences. And that's pretty everything I wanted to tell you about. That's our essentials about safety. What? Sorry, Uncle Bob, of course, there is one section I need to add. The essential of safety is to write unit tests because they are the ultimate check if something works in our application. This section, I decided I cannot finish my book without it, so I added few pages about essentials of unit testing. It's not really Kotlin specific, and for some it might be basics, but I decided it must be there. And what needs to be understood is that unit test is just one layer. It's generally our layer of programmers, because integration tests and UI tests are often handled by testing engineers. It depends on the company. But unit tests is something that helps us a lot, helps us refactor the programs, and also gives us very fast feedback when we do development and help us design our programs better. Unit testing has many advantages. I think you heard about it, but it has also one big flaw, I believe. It is just hard. It needs to be learned. And it's not just writing unit tests, what is relatively easy to learn, but it is designing your system to support unit testing and also designing your unit tests to not constrain your system. This is hard hard ability, but I think it's important ability, it's essential ability that we should all learn to have our programs truly safe. And so this presentation is based on my book, so for the sake of reference, here are all chapters, all items from this chapter. If you want to find this book, it is on LeanPub, and I also made a code that works for a week that gives 20% discount for DroidCon. You just give a link of the book, Effective Kotlin /C/DroidCon London, and it will work. And that's everything from my side. Slides will be published on Twitter like always, and link is there if you want to find it right now. And thank you for your attention, and have a happy Kotlin. I believe I have minutes for questions, 4 minutes for questions. Are there any questions? Okay, so I am around if there is no one to ask.